Okay, hello and welcome to my channel. Today we're gonna talk about the time delay. And remember when we mentioned time delay, we are talking about sending in a wave packet and seeing how it bounced back. There would be time delay. So there won't be any time delay when you just send in like one particle. So when you have a wave packet, remember the Fourier transform. So I'll just write it down real quick. This is, so we're gonna take the time evolution. There we go. And next is the outgoing wave. And for the outgoing, we assume that it's gonna bounce back perfectly, meaning our phase shift is gonna be -1. So I will not write the phase shift, instead put a -1 outside. Okay. Alright, ET over H bar. Okay, so this is your Fourier transform. And remember the assumed to be stationary around K0, or the stationary phase approximation. You would get that your incoming wave is equal to V group T, and your outgoing wave here is V group times T minus 2H bar, the derivative of your delta. Delta now is a function of K. Alright, so once you have this, okay, this is a minus as we're sending it in on the other side. Okay, right, so now you have this. This term now would be different from this term by a factor of 2H bar, the derivative of delta of K. Therefore, you can say that your difference in time, or the time delay, is equal to 2H bar, the derivative of delta over K. Okay, I should just say d delta dk. That would be way easier to say. D delta dk. Okay, and from here, I'm gonna split it up into d delta dk, d delta dk, and put in a dk dE. Okay, now you can take this term, put it down here over to the denominator of the 2. So here we take the H bar down to cancel out the H bar that we get from the dEdk. Okay, and now we left with this term here. Okay, so with this you can pull this term away and get 2V group d delta dk. Right, from here you introduce the range of interaction, well, the range of your potential v of x. I might just draw it out. Okay, so I will take my range. So for example, you have some sort of potential here. So this is the range of interaction. I don't remember the name, so I will take 1 over r, the derivative of delta k, to be equal to 2 over 2r over v of x, vg. Okay, and this guy here is called the Figner's time delay. Alright. So that is what we have now. Now from this we can figure out a lot of things. So basically in a problem, what you want to do is get your delta, and you can get almost everything in that problem already. And most of these problems are going to ask you to plot it. So we're going to take a look at an example here. Example. So example, your potential is going to look something like this. Let's point to A. The potential is going to be a 3 region. To look at it is, of course, 0 when your x is less or equal to 0, mean infinity. This is, take this minus v naught when it is between 0 and a, and over a it is nothing. Okay, so that would be your potential. Now, what would be our wave functions? So wave function. Wave function here, it would be 0 when x is greater or equal to 0, as the potential is infinite. In this region, we take k prime. This is k. Okay, so in this region, you can see that it vanishes at 0. So intuitively, you're gonna think that only the sine function would remain, and indeed it is the sine function x a. And on this side where the potential is now 0, it is equal to, well, ei delta sine kx plus delta, and this is universal for this sort of system that you have here. Okay, so once you have this, you just apply the continuity. So at psi and psi prime, so continuity t at x equal a. So this is a sine k prime a equal to e delta sine ka plus delta. This is ka cosine k prime e k sine ka plus delta. Okay, now you divide it to get a cotangent. That term is gone. Cotangent k prime a. This term is k. It's cosine, I'm sorry. Cotangent ka plus delta. Right, so once you have this, you can now, well, expand it and put in your unit-free number, and eventually you would get your tangent of delta, and that would equal to something that could be very messy, and indeed it is very messy, so I probably won't write it out right now. And once you have this, what you can figure out is these. So the first one is the phase shift. Now it would probably, in terms of u, because you put them in the unit-free numbers, Next one is the internal amplitude, the probability, and the Wigner time delay. I'll put it as R. Yeah, just that. Okay, so these would be your plots, and we're gonna take a look at these in a later example. I will make a separate video for that, as well the first time you look at it, it won't be easy to understand, even comprehend. Well, it took me like 3 weeks to grasp what this means. So I will make a separate video on that example. And okay, that will be the end for today. Goodbye.